All right, welcome back. In this video, we'll start our quick look at arc cosine. We covered arctan and arcsine extensively. Those are going to be the main inverse trig functions that we'll need this term. Our arc cosine we'll use a bit, so I'll go through it, but it's really close to what we've done for arctan and arcsine, and so we won't go into as many details. So I'm going to start with a graph of cosine and its potential inverse, and I'm going to look at which interval we could restrict cosine to ensure that it passes the horizontal line test. All right, so cosine is a lot like sine. It's a wave, but it starts at 1. So here I have 0, 1, and then it plunges on either side like this, like that. So this here is minus pi onto 0. This one is pi onto 0. And then it goes here to negative 1 at pi and at minus pi. All right, so already you can see that it doesn't pass the horizontal line test as I have multiple intersections between this line and my graph. Let me graph the potential inverse. So instead of 0, 1, I'm going to have 1, 0. And then this point here is going to land here at 0 pi on 2. And I'll have 1 on the other side at 0 minus pi on 2. And then I'm going to be here at minus 1 pi, and then here at minus 1 minus pi. All right, let me graph it. It's going to look like this, and like this, and then it's going to come back up. All right, so this is the potential inverse. Of course, it's not a function because the original function didn't pass the horizontal line test, so I need to restrict it. I need to restrict it to a smaller domain on which it would pass the horizontal line test. And so I'm going to start at 0, 1, but now notice that I can't use both sides because if I start going this way and going that way, I'm going to actually fail the horizontal line test. So I'm going to start here and I'm only going to use positive value. We're picking positive value because we like them better, not because they're intrinsically better. And I'm going to go up to this point. As soon as if I were to go a bit further, I would actually hit the same values twice, so I can't do that. All right, so we're going to start here and go here. And so we'll restrict the cosine graph to angles in, all right, so we're going from 0 to pi. In 0 to pi, those points are on the graph, and so we'll include them. We restrict cosine angles from 0 to pi. It will then pass the horizontal line test. And I will get this part. So this yellow, actually, let me put it green as well. So this part here, that would be the graph of arc cosine of x. So arc cos is the inverse of the function f of x equals cosine of x for x in set 0 to pi. All right, and then from the definition and from section 1.1, we know that arc cosine of x equals theta exactly when x equals cos theta, and then theta is in 0 to pi. Note that when we ask for arc cos of x, then we're giving you the cosine value. X is the cosine value, and we're asking for the corresponding angle. Remember that cosine corresponds to the x coordinate. All right, so this is the one where the x makes the most sense. For arcsine, it was the y coordinate, but we still use x as a variable for the function just because of graphing. All right, to evaluate arc cos, we do the same thing as we've done in the past. There's just one little caveat, a little difficulty that we didn't have before. So we find theta first so that cosine is equal to absolute value of x. If x is positive, then we're happy. That's going to be our answer. Now, if x is negative, that's where things get a bit tricky. All right, so we have this angle theta that gives us absolute value of x. Now we want to get this value here. And so the angle we want is this one. The way we'll do it is we'll actually look at pi and then come back minus theta. Like this. All right. So that's going to be pi minus theta in the case of negative. So this one is pi minus theta. All right, so I'll try two examples. Arc cos of root 3 on 2, x is root 3 on 2, so is absolute value of x. And so root 3 on 2, I take the cosine, I have root 3 on 2, I'm going to get pi on 6, and so theta is pi on 6, which means that arc cos of root 3 on 2 is pi on 6. Now, for a negative value, I just need one extra step, so everything else is the same. I get theta equals pi on 6, and now when I compute arc cos of root 3 on 2, I'm not going to give you pi on 6. I'm going to take this formula here, pi minus pi on 6, and so that's 5 pi on 6. All right, so negative values is a bit trickier for arc cosine than it was for arcsine and arctan, but let me show you where these angles are just to make sure you agree with me. So this is pi on 6, so this x value here is root 3 on 2. If I take 5 pi on 6, it's going to be that angle. And notice that I have an extra pi on 6 here, and so that's where we got our formula. And then this angle here will be minus root 3 on 2. All right, so this is how we define arc cosine. There are 3 other trig functions, and so 3 other inverse trigs. So similarly, we can define the inverse of each trigonometric function. So we could define arc secant, we could define arc cotangent, we could define arc cosecant. Arc secant would be the inverse of the secant function. You'll have to restrict the domain as well. So the domain will have to be between, this is crazy though, 0 to pi on 2 excluded, pi on 2 excluded, pi and union. And so you can see that it gets a tiny bit more complicated just because these functions are not always defined. Cotangent is not so bad, it's from 0 to pi, looks a lot like the arc sine. And then arc cosecant is the inverse of cosecant on, again, some crazy interval. All right, so these functions, we will not consider this term. So just for your information, they exist. You might see them at university at some point.